Okay, so let's get started. In today's experiment we are going to see some of the audio effects that we can implement using MATLAB. So in this experiment we are going to implement saturation, echo, then we have reverberation effect, then after that we are going to look at flanger effect and the wah-wah effect. Okay, so saturation is let me start with saturation effect. Saturation is simply clipping off the signal beyond certain limits. So this introduces certain new harmonics into the signal, because of which different type of texture is given to the output signal. So constructing this in the Simulink models, here we have a speech file generator, then we have a clipping filter. Basically you can see that it saturates at two limits, and then we are going to see it at the output. So let me run this.
The discrete Fourier transform of a real-valued signal is conjugate symmetric. The discrete Fourier transform of a real-valued signal is conjugate symmetric.
So as you can see, the waveform here is clipped between the two limits, and this is what the effect of clipping occurs. This is in the amplitude form, and you have just heard the audio as well. Okay, so we now move on to the next effect, which is the echo effect. Okay, so construction of echo is very simple. All we have to do is take the waveform and then delay it a little bit and add it to itself. So basically it means that maybe the waveform, maybe the sound that you have created has got reflected back from certain surface, and after certain delay it has again come back to you. So this can be simply modeled as y of n is equals to x of n plus a x n minus t, where a is some constant between 0 to 1, or whichever way we want. By adding the delay copy of the signal itself, we generate the echo effect. So this, let me again start it. Okay, so let's run this and see what kind of effect we see in the output signal.
The discrete Fourier transform of a real-valued signal is conjugate symmetric. The discrete Fourier transform of a real-valued signal is conjugate symmetric.
So this was the delay effect, and based on this delay element value, we can actually increase the echo effect also. So there will be definitely a lot of difference when you increase the value. Okay, so let's run this code again.
The discrete Fourier transform of a real-valued signal is conjugate symmetric. The discrete Fourier transform of a real-valued signal is conjugate.
So this was the delay effect, the echo effect. Now in reverberation is very similar to echo effect. However, it is consisted of multiple echoes that add up together in certain form. Let me show the signal model. Okay, so you can see that multiple copies of the signal in delayed manner, x n minus d, where d represents the delay. Then we have multiple copies with more and more delayed versions being added up, in a form of geometric progression, where the coefficients are basically varying in a geometric progression manner, and as higher powers of a are multiplied, are taken as coefficients, their value diminishes. The value diminishes. Basically, it means that the signals with the much large delay are very much diminished in amplitude as mod a squared less than 1. This can be written in a recursive format like this, and so as the statement is mentioned over here. So we are going to implement this same thing into a Simulink here. So let me just do it. So okay, so same thing is performed, where a in my case I have kept 0.5, and this is the delay value. So let's hear the effect. This is the reverb effect we are saying about.
The discrete Fourier transform of a real valued signal is conjugate symmetric. The discrete Fourier transform of a real valued signal is conjugate symmetric.
Okay, so now let's move on to the flanging effect. So flanging effect, it's difficult to directly say it, but it introduces the same version of signal into itself. However, as the signal proceeds with the time, the added signal, or the delayed version of the signal that is added to our original signal, varies in the delay value. So this we are implemented using a fractional delay unit, and then there are basically, to vary the amount of delay, we are going to use a sinusoid here as a reference, which varies slowly of 1 Hertz. So the net effect of flanging can be seen as if there is some metalish sound added to our speech signal. So this is the entire block for implementation. The flangers statement, the mathematical description of a flanging statement is given like this, where the delayed version of signal which is added, that part's delay amount is varied as a function of n itself. So this is the flanging. So let's see the Simulink implementation here. So this is the what I have done. Alright, so let's implement it.
The discrete Fourier transform of a real valued signal is conjugate symmetric. The discrete Fourier transform of a real valued signal is
Alright, so as you could hear, there was some kind of metalish effect added to the original signal itself. That is the flanger. Now the last part of our experiment, which is going to be the wah-wah effect. The wah-wah effect is modeled in this way. Okay, it's not mentioned here. Okay, so in this case we are having certain technical issues, but a wah-wah filter works in this way. Basically, what we are going to do is that we are going to pass the signal and add a signal to itself by passing it through a band pass filter, which has a very narrow band, and this bandwidth of, or the range at which the filter is performing the action, is varied with time. Basically, what we are trying to say is that the resonant frequency of this band pass filter is varied over time, so that some kind of wowing effect is added onto the original signal. So this is the entire implementation, where this is the entire band pass filter implementations, and this is a reference signal generator so that your frequency can be shifted. So let's see its effect. So this was the effect of wah-wah. In general, in implementing in many equalizers, all these effects are combined so that equalization is achieved. Thank you very much. Thank you.